you very much. Yeah, thank you very much, Paolo, for inviting me, and thank you everyone for coming. So this seminar is on variational methods for conditional volatility forecasting, and this is a joint work with my supervisor Paolo. So this is how the seminar is structured. So we start by giving a brief background on why we do volatility forecasting and what are some of the challenges associated with forecasting methods. We talk briefly on the existing methods, which are the GARCH models and the stochastic volatility models. So many of you might be very familiar with GARCH models that are used very extensively in industry, but also stochastic volatility models that are not used very often, but they offer a very appealing alternative. And lastly, we talk about the two models that we would like to add to the literature. So the first one being Neural-GARCH, which is a neural network adaptation of traditional GARCH models. And we think that it's best used in lower dimensional settings. We'll talk about why in a minute. And by low dimensional settings, we mean roughly below five assets. And the second model that we like to present is called Variational Heteroscedastic Volatility Model. And for this one, we think that it works best in higher dimensional settings because it directly forecasts the covariance matrix. And by higher dimensional, we mean that anything that the Neural-GARCH can't handle, which is roughly greater than five assets. So to start with the motivation and mathematical framework, so we fit everything into a page. So we think that obviously from surveying the literature, modeling volatility or heteroscedastic behavior in financial time series is obviously important in domains such as asset pricing, risk management, or portfolio optimization. So for example, to compute the value at risk, we need to have access to the covariance matrix. And when we do things like dynamic portfolio optimization, we also need access to the a forecast of the covariance matrix. So just very briefly, so if we have an asset with price ST, then we can compute the log returns. So we use RT to represent log returns for the remainder of the presentation. So we compute the log returns and we assume normal innovations. So we assume that these log returns are normally distributed with a mean of 0 and some sort of standard deviation, which varies with time. But obviously there are other choices of innovations. So for example, we know that returns often exhibit excess kurtosis, or what's commonly known as the fat-tailed behavior. So you can use other distributions or other innovations like the student's T distribution, which we will consider in some of our experiments. So this is in the univariate case, but in the portfolio of assets, in a portfolio of n assets, for the remainder of the presentation, again, we use small n to represent the dimension of the portfolio. We assume that the returns, which is now a vector, follows a multivariate Gaussian distribution that is parameterized by mean, a zero mean vector, and some sort of time varying covariance matrix, where this covariance matrix is n by n. I think it's worth distinguishing between the unconditional mean and the unconditional moments and the conditional moments of a time series. So the unconditional mean and variance are simply the expectation of RT and the expectation of RT squared. So if we look at the diagram on the right, which is basically just the returns time series of an arbitrary asset, the unconditional mean, we see that is basically 0, and the unconditional moments are basically the moments of the returns if we were to collapse all the data points onto the y-axis. So the unconditional moments are not time varying, so they are constant quantities. So they're not very useful in terms of forecasting. So in our work, we are focusing specifically on the conditional moments, which is basically if we have a sequence of observations, we're interested in the distribution of the return for the next time step. So if we consider an information set which has within the set a sequence of returns and a sequence of conditional volatilities, we would like to forecast the expectation of RT squared conditioned on this information set, which is the sigma squared T. So this is again in the univariate setting. In the multivariate setting, we would have the covariance matrix. So why is volatility forecastable? Well, we know from surveying the literature that there's something known as the volatility clustering, which are basically these circled regions in this diagram. And it's simply saying that regimes or timestamps of high volatility tend to be followed by similar high volatility regimes. And similarly, there's also something known as the spillover effect, which is basically the transfer of shock between financial markets, which basically means that we can use information that we have on other markets to forecast the conditional volatility of the asset that we're interested in. So this summarizes the motivation and the mathematical framework. So this slide is on existing methods that people use to forecast conditional volatility. So the first class is the GARCH models, and the second class is what's known as the stochastic volatility models. And they are often considered to be two competing classes of models, because the GARCH models are conditionally deterministic. So if we just look at the expression for a very simple GARCH PQ model, where P and Q represent the lags of the ARCH term and the GARCH terms, we see that given these model coefficients, omega, alpha, and beta, and also the observations and the previously forecasted variances, we can deterministically compute the forecast for the volatility at the next time step. And usually these models are trained with maximum likelihood, but the main problem is that they suffer from cursive dimensionality. So they have a computational complexity of n to the 5. So n is the number of assets. And it's been documented in some papers that the maximum dimension that a GARCH model can handle is roughly 5 assets. So that's where the 5 comes from in the previous slide. Stochastic volatility models express an AutoRegressive process in the log volatility. So we use HT to represent the natural log of the variance. And we see that due to this stochastic error term, the evolution of the log volatility is a stochastic process as opposed to a deterministic process in the GARCH model. So that's the main sort of difference in the underlying assumption. The main difficulty of the stochastic volatility model is that the posterior of the model coefficients given the observations RT are often intractable, and therefore we need to rely on things like Markov chain Monte Carlo samplers to approximate the posterior distribution. And also, until very recently, there was no sort of open source software that people could use to estimate these models. But there are now the StochVol and the factor StochVol packages in R, which have been recently developed, and that's what we use to run the baseline models in our experiments. And also, these models are slow in convergence for high dimensional problems. So we see that for these two existing models, they tend to sort of fail in higher dimensions, and they assume fairly simple functional forms in the temporal dynamics, and that's why we wanted to sort of introduce deep learning to basically alleviate these issues. So we identified three main challenges that are associated with volatility forecasting. So we will go through each of the three sequentially. So the first one is, how do we infer a latent time series from a noisy observational time series? Because the conditional volatility process is a quantity that we're interested in, but it's something that's not directly observed. What we do observe is the observational returns time series. So we need to be able to go backwards and infer the latent variable from the observational variable. And also, how do we model the nonlinear dynamics in the temporal domain? The second challenge is, we know that a covariance matrix must be both symmetric and positive definite. So this is those two constraints need to be applied to the neural network output. But how to apply those constraints are sort of challenges that we were trying to deal with. And the third challenge is, how do we alleviate the computational burden associated with maximum likelihood estimation? So this is more concerned with higher dimensional settings. So we will cover each of the challenges. So we start with the first one. So how do we infer a latent time series from an observational time series? The way that we do it is through variational inference. So if we look at variational inference in a static setting, if we assume that we have observational time series xt, which in our case would be rt, which are the returns, and a latent time series zt. So we're interested in the potentially intractable posterior distribution p theta z given xt. So we would like to infer zt given xt. But this posterior is often intractable. And what we do in variational inference is we use a much simpler distribution, which we call q of phi, z given x. This could be, for example, a Gaussian distribution. We use this simpler distribution to approximate the true posterior distribution, which is the p of z given x. And this is this whole framework is done using a variational autoencoder. To find the model parameters, we would like to maximize the log likelihood of the data, which is just log of p of rt. And if we look at this diagram on the lower right, we see that the distance that we're trying to maximize is this log p of x given theta, where theta is the model parameter, and it can be expressed as the sum of an evidence lower bound, which is this L here, and some sort of KL divergence between Q and P. So that's given by this formula here, and we see that the marginal log likelihood is only expressed in terms of theta, but the elbow and the KL divergence both have the parameter phi. And phi is the parameter of the variational approximation that we're using to approximate the true posterior. This means that with respect to phi, maximizing the elbow is equivalent to minimizing the KL divergence between the variational posterior and the actual posterior, which is what we want because we're trying to approximate P with Q. And KL divergence is a statistical distance between distributions. So by having a small KL divergence, we have a fairly good approximation of the posterior. So that's basically what we're doing with variational inference. But this is variational inference in a static setting. In terms of time series, we're interested actually in the posterior filtering distribution, which is P of Z given X from 1 to T. So we'd like to infer the latent random variable given a sequence as input, as opposed to just a one-time step. There are also other types of posteriors, such as for example, the smoothing distribution, which is P of Z given X from 1 to big T. And that's basically inferring the latent random variable at a certain time given the entire sequence. But in this particular paper, we just focus on the filtering distribution. And in order to model the nonlinear dynamics in the temporal domain, we use a recurrent neural network, a fairly common choice. And a recurrent neural network with hidden state HT, such that P of ZT given X from 1 to T is equal to P of Z given HT. So because recurrent neural networks have memory, we think of the hidden states as a summary of what has happened up to that time step. So we use the hidden state of the recurrent neural network as inputs into the variational autoencoder, which allows us to parameterize these posterior distributions. So moving on to the second challenge, which is how do we parameterize a valid covariance matrix? So there are two different potential solutions that we can think of. The first one is we can combine traditional econometrics models with neural networks. So by traditional econometrics models, we mean the GARCH models and the stochastic volatility models. And the advantage of this approach is that the traditional GARCH models, they have very well-behaved mathematical properties. So by design, they ensure, so they're often expressed in terms of some sort of recursion. So you input the previous observations, and the equation tells you what the next covariance matrix should be. So by design, the GARCH models give you valid covariance matrices. But they often assume fairly simple functional forms. So by combining traditional GARCH models with neural networks, we can augment the well-behaved statistical properties of these econometric models with the modeling capabilities of neural networks. So that's what we have done in the Neural-GARCH model, which works in low-dimensional settings. The second potential solution is we basically completely abandon what we know from traditional econometrics, and we just follow a purely data-driven approach. And in that stream, we have to find another way to parameterize the covariance matrix. And this is something that we will talk about in the second model. And the third challenge is how do we alleviate the sort of the computational complexity. So we know that we train the model using maximum, well, we find the parameters using maximum likelihood. And we will see later on that in the multivariate Gaussian case, we need to invert the covariance matrix, which can be very computationally expensive. So we need to find a way to alleviate that problem. Okay, so we talk about Neural-GARCH first. And the intuition is very simple. So we've given here the traditional GARCH 1.1 model and the traditional multivariate Beck 1.1 model. So these are two of the commonly used GARCH models. So we see that they both have constant model coefficients. And our intuition is basically we make these coefficients time varying, and we use neural networks to parameterize these time varying coefficients. And our intuition is that by making these coefficients time varying, we can better accommodate these constantly changing dynamics that we observe. So we define a vector called gamma t. So in the univariate case, gamma t is a vector of 3 elements, which is basically omega t, alpha t, and beta t. But of course, gamma t depends on the choice of the GARCH model. So in our case, we've chosen Neural-GARCH 1.1 and the Beck 1.1. But of course, you can choose, for example, the E-GARCH model or the JGR-GARCH model. So it's completely up to the user. And in the multivariate setting, gamma t is a vector of matrix elements. So big omega t, at, and bt are matrices of the Beck 1.1 GARCH model. So basically, we break down the matrices into vectors. And we would like to infer gamma t using observational time series. So we perform recursive prediction and inference of gamma t using our designed neural network. So this is basically the framework of Neural-GARCH. So there are two model components. So one is called the generative model, which we show in this page, and the other one is the inference model. And there are two different models because if you think of a variational autoencoder, which we have shown here, it has an encoder neural network and a decoder neural network. So the encoder neural network infers the latent random variable given the observation. And the decoder takes as input the latent random variable and it tries to reconstruct the original time series. So that's why there are two model components. So you can think of the generative model as the decoder. So the generative joint distribution is P of R, which is the returns from 1 to T, and sigma, which is the sequence of current covariance matrices, and gamma from 1 to T, which is the sequence of time-varying model parameters of the GARCH model. So we have some initial value that we can set for the model parameters, some initial value for the covariance matrix. And we have here P of gamma T given gamma T minus 1, and R from 1 to T minus 1. So this is the most important component of the generative model because, and it's also shown in this diagram here, because this is what's responsible for making the predictions. So if we look at the diagram, this distribution is parameterized by this multilayer perceptron. It takes as input the previously estimated model coefficient, gamma T minus 1, and the hidden state of the RNN from T minus 1. And as we said previously, this HT minus 1 is a summary of everything that has happened up to T minus 1. So you can use it as a proxy for R from 1 to T minus 1. And so P of gamma 0, this is, we've set it to a vector of 1s, and P of sigma 0, this is just the covariance matrix that we estimated using the training set. And from this distribution, we can predict our estimate of the model parameter for the next time step, given gamma for the next time step, along with our observation RT minus 1 and our previously estimated covariance matrix. We can deterministically compute what the next covariance matrix should be, because this distribution is just the choice of the GARCH model. So in our case, we chose the GARCH 1-1, but as I said, it could be the eGARCH or it could be the JGR-GARCH. And once we estimate the covariance matrix for the next time step, we can deterministically compute this distribution, which is basically just the log likelihood function. So it could be the multivariate normal distribution, or it could be the student's T distribution if you want to directly account for the excess kurtosis in the returns. So this is the generative model. The inference model is you can think of it as the encoder of the variational autoencoder. So this parameterizes the posterior distribution of the sequence of covariance matrices and the sequence of model parameters, given our returns time series, which we directly observe. So again, we now try to infer gamma T conditioned on the previous model coefficient, but now we have access to the entire returns time series. So before we had R from 1 to T minus 1, and we're trying to forecast the next step model coefficient. But this time, because we're performing inference, we should have all the information that we need to infer the posterior estimate of the GARCH parameters. And this Q phi distribution here is exactly the same as this distribution, because it's simply the choice of the GARCH model. So the main difference is that in this case, we are predicting what the next gamma T should be. And then we are looking, and then we're computing the likelihood function to see how well our estimated distribution fits our observations. But in this case, we're performing inference. So we're trying to go backwards And then again, we use this to compute the deterministic covariance matrix from the choice of the GARCH model. So this distribution is shown in this diagram. So it's a separate multilayer perceptron. It takes as input the previously estimated model coefficient gamma t minus 1 and the RNN hidden state HT, and it parameterizes the distribution over the posterior estimate of gamma t. And to train the model, we maximize the evidence lower bound, which is given here. And theta represents the parameters of the generative model from the previous page, and phi represents the parameters of the inference model. So we optimize over both models simultaneously. So this term, the first term is log p of RT given gamma t. This simply tells us, conditioned on our estimate of the model parameters, how well the estimated covariance matrix fits the observed returns time series. And this KL divergence is between the posterior distribution of gamma t and the prior distribution of gamma t. This is almost like sort of aligning our prediction network with the inference network. So these two pages summarize the model components of Neural-GARCH, and it's basically we make the model parameters of the GARCH model time varying, and we use a neural network to predict what the future model coefficients should be. So we ran some experiments on foreign exchange time series and also some stock indices and some commodities. The frequency of our data was daily returns, daily log returns, going back roughly 10 years. So on this page, we show some multivariate Forex portfolios and some univariate Forex time series. The numbers that we have in the table are the log likelihoods. So the larger the log likelihood, the better. And as baselines, we have the traditional GARCH 1.1 with normal innovations, the GARCH 1.1 model with students T innovations, and then our model with normal and students T innovations. And in the univariate case, we also show the eGARCH model. So the eGARCH model explicitly accounts for what's known as the leverage effect, which basically means that it accounts for the skewness in the returns distribution. So for the Forex data, we see that our Neural-GARCH model performs fairly well, and it's this improvement over the traditional GARCH models is fairly sort of consistent across the experiments that we've run. On this page, we show some commodities time series and also the stock indices that we considered. But in this case, especially in the stock indices, we get fairly mixed results. But this is within our expectations because we know from the literature that stock returns time series often exhibit leverage effect, whereas foreign exchange time series rarely exhibit any leverage effect. And because our Neural-GARCH model in our experiment is a direct adaptation of the GARCH 1.1 model, that's why we get consistent improvements in the foreign exchange data set because there's no leverage effect. But in the stock returns time series, the eGARCH performs fairly better because it is a model that's designed to account for the leverage effect. But we are expecting that if we construct a neural eGARCH model, we're fairly confident that it should be able to outperform the traditional eGARCH model. And just to further aid the analysis of the previous log likelihoods, we computed, or we drew these critical difference diagrams. And what they show is the average ranking of the different models across the experiments that we've run. So for example, the Neural-GARCH 1.1 model with students T distribution has an average ranking of about 1.8. And also these horizontal black lines represent the fact that there is no statistically different, no statistically different in performance across the experiments that we've run. So for example, we see that in these 4 models, there is no significant difference, whereas the Neural-GARCH model is, at least from the experiments that we've shown, performs fairly consistently better than the rest of the models. And in this case, so this one is only for the univariate experiments, but in this case, we show across univariate and multivariate. And we see that the Neural-GARCH 1.1 model with students' t distribution performs the best out of all the models that we considered, which is in line with literature that students' t distribution can better accommodate the excess kurtosis that we have in the returns time series. So we've gone through the first of the 2 potential solutions to parameterize a valid covariance matrix. We now talk about the second one in conjunction with how to alleviate the computational burden associated with maximum likelihood estimation. So this is the second of the 2 models that we would like to add to the literature. So again, we assume that our multivariate returns follow a multivariate Gaussian distribution, and we're interested in forecasting the covariance matrix. To do maximum likelihood estimation, so we've shown the expression here, we need to compute the log of the determinant of the covariance matrix and what's known as the Mahalanobis distance. And it is the second term that's very computationally expensive, because we see here that we need to invert the covariance matrix for every time step. But what we can do is we can make the precision matrix, which is the inverse of the covariance matrix, the output of our neural network. This simple change allows us to completely bypass the matrix inversion step during model training, because the computation of the Mahalanobis distance is simply RT times whatever the neural network output is times RT. And in the test set, if we would like to have access to the actual covariance matrix, we can then invert whatever the neural network outputs. So the way that we parameterize the covariance matrix is through a Cholesky decomposition on the inverse of the covariance matrix, which is the precision matrix. So we know that the inverse of a symmetric matrix is symmetric, and the inverse of a positive definite matrix is also positive definite. And these 2 properties are useful because they allow us to simply constrain the output of the neural network, which is the precision matrix, and be confident that the resulting covariance matrix is also symmetric and positive definite. And what we do is we decompose the precision matrix, denoted PT, using a Cholesky decomposition, LT times LT transpose. So this LT is a lower triangular matrix, and therefore LT transpose is an upper triangular matrix. So the decomposition of a matrix through Cholesky decomposition ensures that the resulting matrix is symmetric. And to compute the first term, which is the log determinant, we can simply compute -2 times the sum of the log of the diagonal elements of this matrix LT. And as I said, if LT is lower triangular, then it guarantees that PT is symmetric. But of course, neural networks can't directly output a matrix. They output a vector of values. So we need a deterministic way to convert a vector into a matrix. So the output of the neural network is ZT, which is a vector. And we say that ZT is the vec operator applied on the lower Cholesky decomposition of the precision matrix. So the vec operator is very often used in econometrics. So if we look at this example here, the vec of a lower triangular matrix simply gives you a vector of the non-zero elements. So this vector of values would be the output of our neural network. And we use the inverse of the vec operator to arrive at the lower Cholesky decomposition of the precision matrix. And the last thing we need to do is we need to make sure that the precision matrix is positive definite. And that can be achieved by applying a soft plus function, which is given by this expression here, to the diagonal elements of the of this lower Cholesky decomposition. So to summarize, the output of our neural network is a vector, which is ZT. So we first convert it into a lower triangular matrix in a deterministic manner. And then we identify which elements are the diagonal elements. And then we apply a soft plus function on those elements to ensure that the precision matrix is both symmetric and positive definite. As with the Neural-GARCH model, the VHVM model also has two components, which are the generative and the inference models. So the generative model parameterizes the distribution of R from 1 to T, and the lower Cholesky matrix from 1 to T, and the neural network output, which is the latent space of the variational autoencoder from 1 to T. So P of ZT given R from 1 to T minus 1, this is again our prediction network that's shown in the diagram on the right. We also call it the prior distribution. And it's a multilayer perceptron. It takes as input the hidden state of the R and N from the previous step, and it parameterizes a normal distribution for the latent random variable ZT. And given ZT, we can deterministically compute the lower Cholesky decomposition because it's simply the vec operator followed by the soft plus function. And given the lower Cholesky matrix, we can compute the log likelihood. So it could be a multivariate normal, it could be a multivariate student's T. So given LT, we can multiply it by its transpose to obtain the precision matrix. And we've seen from the previous page that given the precision matrix, we can directly compute the log likelihood function without having to invert any matrix, at least in the training phase. The inference model parameterizes the posterior distribution of the lower Cholesky matrix and also the latent space of the variational autoencoder. So we have Q of phi of ZT given R from 1 to T. So rather than T minus 1 from the previous page, we now have 1 to T, because when we infer ZT, we should have access to all the necessary return time series. So that's given by this diagram on the right, and is a multilayer perceptron model. It takes as input the hidden state of the R and N, HT, which is a proxy for the returns time series R from 1 to T, and it parameterizes the posterior distribution of the latent random variable. So you can think of this as the encoder of the VAE, or the variational posterior. And again, this Q of L given Z is the same as this P of L given Z, because it's simply a deterministic function that we use to transform our neural network output from a vector to a matrix. And similar to the Neural-GARCH model, we maximize the elbow objective function given by this expression here, where we maximize the log likelihood of RT given ZT, and minimize the KR divergence between the prior and the posterior. So for the experiments, we compared our model against 3 other models. So we chose the DCC-GARCH model from the GARCH class. We chose this one because DCC accounts for dynamic conditional correlation between assets. We chose a Markov chain Monte Carlo stochastic volatility model using the factor vol package recently developed in R, and also a state-of-the-art deep learning model called the Neural-Stochastic Volatility model. So we demonstrated our model on multivariate FX portfolios. So these are daily returns going back 10 years. And so here we have some 5-dimensional portfolios denominated in euro, denominated in GBP. And in the first column, we have our model, and then the rest of the baselines. Some more results for other currencies, also 5-dimensional data sets. And to summarize, we have basically plotted everything into a critical difference diagram. And we see that this time there is a significant difference between all of the models that we tested. But in general, our model performed best, followed by the Markov chain Monte Carlo stochastic volatility model, and then followed by the GARCH model, and lastly, the deep learning model. And the reason for the deep learning model performing worst, we think it's due to the fact that it's overly parameterized, and therefore it may have caused some sort of overfitting. And in addition to the 5-dimensional data sets, we also conducted some 10-dimensional, 20-dimensional, and 50-dimensional experiments. And in these high-dimensional experiments, we only compare against the deep learning baseline because the GARCH model and stochastic volatility models can't be generalized to higher dimensional settings. So to summarize, our main contributions are 2 end-to-end neural network architectures that are capable of modeling heteroscedastic behavior in financial time series. And the Neural-GARCH model is designed to work in lower dimensional settings. And because it's a combination of traditional econometrics models and neural networks, they are more interpretable in the sense that you know which phenomenon you are accounting for explicitly, but they also suffer from the same drawbacks as the traditional GARCH models, which is the curse of dimensionality. So they're often used when we have less than or fewer than 5 assets. The other one is the variational heteroscedastic model. We've designed it to work in higher dimensional settings. So in our case, we tested up to 50 dimensions, but we are fairly confident that it can generalize up to at least 300 dimensions. And we know this because a paper from computer vision used a fairly similar scheme to parameterize the covariance matrix. And because this is an n-squared algorithm, they estimated a vector of about 100K in dimension. So if you take the square root of that, it should give you about 300 assets. And also, we identified these 3 challenges associated with volatility forecasting, and the 2 models that we proposed to a certain extent are able to address all 3 challenges. So that's the end of my presentation. Thank you for listening, and feel free to ask me questions.